Welcome to Astro 101, the Sun and its Neighbors. I'm Professor Bart Netterfield. I can't believe this is already the last class in a really, really fun semester. Today, we're going to be talking about this question of, are we alone in the universe? So far, we've been looking at our solar system. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, the Sun, the dwarf planets. And there's a few things we may have been struck by. First of all, just how vast the solar system is, how vast the universe is. And secondly, how uninviting how the rest of the solar system seems to be, whether it be the vacuum and baking sun on Mercury or the ice on Pluto. Everywhere we've been, everywhere we've seen has been inhospitable, uninviting, incompatible with human life. Everywhere except this one small planet, the Earth. And so this can become to bring up the question, are we alone? Are we all there is? Is Earth the only place? Or is there other life in the universe? Today we're going to try and explore that question. So the first thing, and we've kind of been exploring it the last couple of weeks, the first thing we tried to address is, are there other planets? And so we looked at a few ways that astronomers have developed in order to try to see, are there other planets? The first one is kind of the obvious one, which is, well, just go take a picture of a star and see if there's planets around it. But as you remember, that turns out to be very, very difficult because stars are incredibly bright and planets are very dim. And so when you go to look at a nearby star, you end up seeing mostly diffraction from the telescope, blinding out any hope you would have of seeing a planet. The planet, of course, would be way down in here in the center, completely blinded out. But we learned how, for example, with a James Webb Space Telescope, they can use what's called a coronagraph to block out the light from the sun and then use modeling to remove what's left. And you can hopefully, finally, see maybe down here in the corner, is that a planet? Looks like it. That's something they're working on. This kind of technique has been used to measure something like 100 planets. And it requires planets that are a long way from their host system. The second method we tried to understand is called the radial velocity method. If you recall, when a planet is orbiting a star, the planet doesn't really orbit the center of the star. The star plus the planet together orbit the center of mass of the system. What that means is that when we look at a star with a planet orbiting it, the star will be moving slightly, and we can use that motion using the Doppler effect. We can use the Doppler effect to measure that motion so that we can see the motion of the star. The more massive the planet is, the more the star will move. The higher the frequency the star is moving, the closer the planet must be to the star. So a more massive planet will cause the star to move more. A planet which is closer to the star will cause it to move more quickly. What this means is it's a whole lot easier to measure stars that are close to measure planets that are close to their star and that are massive. The final method we looked at was called the transit method, which is another kind of obvious method. Just look to see if this planet passes in front of the star. If it does, the star's brightness will decrease by a tiny bit, and we can see whether there is a planet. This only works if the orbit of the planet is aligned so that it goes right in front of the star from our point of view. But when it does, we can measure the size of the planet by how deep the dip goes, and we can measure the distance the planet is from the star. If you combine all these together, we can get a lot more information. Recall that a transit method tells us the distance from the star to the planet, that's by the period of the orbit. The radius of the planet, that's by how deep the blip gets, and the orbital inclination, and that is partially by how wide the pulse is. If you combine that with the radial velocity method, which tells us the distance from the star to the planet, again by the period, if we know the orbital inclination, it could tell us the mass, but we know the orbital inclination from the transit method if we get both on the same planet. If we know both, we can know the distance from the star to the planet, we can know the radius of the planet, and we can know the orbital inclination. And finally, we can therefore know the mass of the planet. So with using these both methods on the same star, we can learn a lot about extrasolar planets. So people have been spending the last 20, 30 years, many astronomers have been spending the last 20, 30 years looking for planets, characterizing planets. There's been a couple satellites launched to do this. And here is a census. Oh yeah, and of course you can get the density of the planet. Here's a census of all of the known planets as of November 2025. This is from the NASA Planet Database. And we've got the three types here. We've got transit method planets are in purple, radial velocity methods are in this kind of cyan color, and direct imaging planets we've shown in green. And of course I've also shown our solar system. All planets discovered, this is all the planets have been discovered by radial velocity method, transit method, or direct imaging as of November 2025. Now, many of these, we have measurements both from transit method and radial velocity method, but many of them we don't. We only have the one. When only one is available, we use the size to estimate the mass. Now, that's very uncertain, could be off by a factor of many, but at least gives us an idea. So it's an approximation. So this is all of the planets known so far. Now, there's this whole question about habitability, because the question we've kind of been asking in the back of our heads are we alone? Is there anybody else in the universe? The first thing we want to find out is, are there planets that people could live on if they existed? Or maybe not people, but intelligent creatures. So we talk about the habitable zone. The habitable zone is the distance from a star where liquid water can exist. So we have this band here, distance from the star, and the inner band it would be too hot, and the outer band it would be too cold. Inside the green area, a planet orbiting in there would be able to support water. So a planet orbiting too close to the star would be too hot. Water would all boil and evaporate. There'd be no liquid water on the planet's surface. If the planet was orbiting too far away, it would be too cold. There would be no liquid water, only ice. If you got a planet orbiting right in the habitable zone, then in principle, the planet could hold liquid water. Now, when you do this, you have to account for the greenhouse effect, because greenhouse gases, as you recall, will warm up the temperature of the planet above what it would be with no atmosphere. So we have to do a little bit of fudging here, but when you kind of do those estimates, you come up with a habitable zone, and you can estimate planets orbiting in this region could have liquid water. Doesn't mean they do, but they could if other conditions were right. So the habitable zone, of course, depends on what kind of star you're orbiting. If you're orbiting a bright white star like our sun, it's going to be fairly far away, like the distance to the Earth, to get you into the habitable zone. But on the other hand, if you're orbiting a little tiny, relatively cool M dwarf, then the habitable zone will be very close to the star. That does two things. One is the orbital period will be much shorter, and because it's so much closer, the angles will be easier, and you get much higher detection probability. So it turns out to be much easier to detect planets in their habitable zone around little tiny M dwarfs than it is to detect them around stars like our sun. There's another couple benefits. These little M dwarfs are far, far, far more numerous in the galaxies. There are way more M dwarfs than there were as sun-like stars. And secondly, these little M dwarfs last a very, very, very long time. In fact, no M dwarf has ever run out of fuel. The universe is not old enough. Whereas our sun will run out in another 5 billion years. And it's a third generation star. 2 stars before it have used up their fuel, exploded, and reformed stars. So these little tiny ones last for a very long time and are very, very numerous. And planets that orbit them orbit very, very close, which makes them easier to detect. Now, there's some concern that these tiny little planets, because the planets orbit so close to these tiny little stars, there could be things like solar flares that could serve to sterilize the planets. We don't know, but that's a concern that some people have. Nonetheless, let's see where we are. We want to look at where what of the known planets live in the habitable zone. So I've changed the plot this time. On the x-axis, I've got the temperature in degrees Kelvin. So if you want to get degrees Celsius, subtract 273 from this. So 273 degrees Kelvin would be freezing temperature. This is the mass of the planet in multiples of Earth's mass. This is the temperature the planet would have if there was no atmosphere. That's called the equilibrium temperature. If the planet was just gray with no atmosphere, what temperature would it be? Now it's going to be different because of the atmosphere. It's actually maybe a bit larger than this. In any case, a planet is potentially habitable if, including the greenhouse effect, there could be liquid water. So these two vertical lines are the cold end and the hot end, that a planet without atmosphere, when you put an atmosphere on it, it would be the right temperature for holding liquid water on the surface. Then we want to make sure the planet is rocky and not an ice giant or something like that. So that limits the top mass to something like 3 solar masses. Anything bigger than that, you're going to start producing things like Uranus and Neptune, and it wouldn't be a place with a surface that you could have some liquid water on. It would be some kind of weird ice giant, which is not what we're looking for. And we want to make sure that the planet can hold an atmosphere. If the planet gets too small, say smaller than Mars, the atmosphere all evaporates. So we set the lower limit at something a bit more massive than Mars, so that it will keep its atmosphere so that there can be liquid water on the surface. So any of the planets in this box, we would consider potentially habitable. We'll just say habitable, but we don't know that it's habitable. It means it could be habitable if other things were right. And you see there's something like 6, 7 planets in there. Out of the thousands that have been detected, there's a very few in that little box. So here we are. Those few planets I've now colored in yellow. These are potentially habitable planets. Here's Earth, which would fit in that box as well. So the different stars put you at different radiuses. So, okay. So notice that in our solar system, only Jupiter could be detected. I've colored in the region where our current methods can't detect planets. They're either too low a frequency or too small, or both. Notice that with our current methods, we can't detect Earth or Venus or Mars or Mercury or Uranus or Neptune or even Saturn. We can barely detect Jupiter. So can we do better than this? Why? What's the problem? Well, it turns out that with the radial velocity method, stars have turbulence on the surface. Remember the story about sunspots and solar flares and all these kinds of turbulence going on the surface of the sun? That produced some level of vertical motion. And those instabilities cause vertical motion that shows up as Doppler shifts. And that extra noise masks the radial stellar motion. For transit methods, same kind of problem. Brightness fluctuations, again because of sunspots and solar flares and other solar activities, mask dim transits. And these are intrinsic to the stars themselves. It's not because our instruments aren't good enough. It's because the stars themselves are kind of changing tiny amounts of brightness, kind of flickering a little bit. So better instruments won't work. The only way we're going to get better, if we're going to move into this region, is to have lots and lots and lots of orbits, so we can start to differentiate between the noise and the true planets. And that's going to take years or decades. So that's kind of where we are. It's going to be awfully hard to get into this region. Now we want to know how many, and even down here, these planets, we know it's a lot harder to detect these small ones. We've been able to do it, but we know that we can estimate how hard it is, and therefore estimate the bias, and know that there actually is a lot of planets down here. It's just that we only can detect a very few of them. So we might ask the question then, how many Earth-like planets are there? How many planets in the habitable zone are there? So we can first ask, how many Earth-like planets? That would be planets in the habitable zone around Earth mass that orbit stars that are like the sun. So that might be our first question. We can't detect Earth analogs around sun-like stars, but there's a few things that help us out. First of all, many of these Earth-like planets have been detected around small stars, like all these guys have been detected around dimmer stars. And the other thing that we know is that the Kepler and TESS satellites saw many single transit events. Like it got dim once, but in the lifetime of the experiment, they didn't see a second transit, or maybe if there was one, it may have been confused by fluctuations or noise and stuff. So there's a lot of single transit events, unconfirmed potential planets, and it's thought that there's more than you would expect just from noise themselves. So many of those unconfirmed planets are actually planets we just haven't been able to detect yet. Based on this, people do statistical analysis, and they conclude, based on the number of excess single event stars, planets rather, and based on the number of planets you see around lighter stars, the conclusion they come to is around half of sun-like stars have Earth-like planets. That, combined with the number of Earth-like planets around M-dwarfs, we expect that there are likely around 100 billion habitable zone rocky planets in the Milky Way. How many planets are there in the Milky Way that could potentially be habitable? Based on this census, based on a statistical analysis, the conclusion people have come to is around half. Could be a quarter, could be 3/4, but somewhere around half of all stars have habitable planets. We think it could be something around 100 billion, give or take, habitable zone rocky planets in the Milky Way. That is a lot of potential planets. So which brings us back to the question. There are hundreds of billions of stars in the galaxy and maybe 100 billion habitable zone planets in the galaxy. There are trillions of galaxies visible from the Earth. In all that space, in all that giant universe, is the little tiny Earth the only place with life, or are there any other civilizations? And how would we even answer that question? Well, it turns out there's an easy but kind of unsatisfying answer to the question. Here's the easy answer. It's kind of easy. So track with me, and then we'll decide whether or not we think it was actually the answer we wanted. Current cosmology and measurements and theory suggest that the universe is infinitely large. When we look at the scale of the universe at large scales, we don't see it ending. We can go back in time all the way to the beginning, and everything looks flat and uniform. There's no giant asymmetries. It's symmetric going out. It's symmetric going left, right. We think the universe is likely infinitely large. Now, if it's infinitely large, we would expect that there are an infinite number of stars in the universe. And if there's an infinite number of stars, then there's an infinite number of planets. Now, this we can't know. We don't know what's actually outside. We don't know what's going on at distances further than we could possibly measure. But we can infer that, if you keep going, it's going to be just like this. We don't have any good reason to believe the universe is finite. So modern cosmology suggests that the universe is infinite. It doesn't say it is, because it really might not be. And I can think of some different ways that it could be finite and still consistent with our data. But it suggests that it's infinitely large. Okay, so let's just take that. The second thing is, if civilizations are not impossible, like if the probability of civilization is greater than 0, if civilizations are not impossible, it's the second assumption. Do we think civilizations are impossible? I mean, we exist, so it seems like civilizations are possible. I've got a footnote there. We'll come back to that later. So if you take these two ideas, the universe is infinitely large and civilizations are not impossible, then we conclude there must be an infinite number of civilizations in the universe, because infinity times the probability of that there are civilizations, and this number is not 0, so infinity times a number that's not 0 equals infinity. Infinity times 7, infinity. Infinity times 0.000001, infinity. Infinity times the probability of civilizations, well, that's infinity. So we would conclude from this argument that in the universe, not in the visible universe, but in the entire universe, there must be an infinite number of civilizations, unless A, the universe isn't infinitely large, or B, civilizations are actually not impossible. Now, why did I bring that up? Well, I mean, we're trying to be open-minded here. God can do impossible things. So there are people who believe that God does impossible things, uses miracles to fulfill his purposes, and that the universe, the earth, life on earth, human beings are actually impossible, and God just made them anyway because he's God and can do that. Now, that's not the way I think about it. I see that God typically, almost always, with very few exceptions, follows physics. He follows the rules because they're beautiful. So I suspect that following the rules of physics, civilizations are not impossible. I also suspect that the universe is infinitely large, although it really might not be. Like, that's a wild statement. So, are there other civilizations in the universe? I'm going to lean yes, because I think both of these assumptions are right. If either of the assumptions are wrong, there's no reason to believe that there has to be other civilizations in the universe. So, that's an easy answer, and I'm not sure how rewarding it is, because it's like, okay, there must be, because it's so big. Let's see if we can do better. Instead of asking, because one of the problems is, there could be an infinite number of civilizations in the universe, and the nearest one is 10 times the radius of the visible universe away from us, and there's no civilizations we could ever communicate with ever. Or it could be that there's tons of civilizations everywhere you look. Under every rock and cranny, you find another civilization. We don't know. So, can we make any progress in calculating how many civilizations there are? So there's this thing called the Drake equation. This is a modification of it that Carl Sagan did. It doesn't really matter. I'm going to go with this version. I think it's easiest to describe. We're going to call it the Drake equation, even though it's like the slightly modified Drake equation. The Drake equation tries to calculate maybe something we'd like to know. N, the number of civilizations that could in principle communicate with us. So they're close enough to communicate with us, maybe in our galaxy, and they're intelligent enough to communicate with us, and they're advanced enough to communicate with us. How many civilizations are there that could, then necessarily would, but could communicate with us? Well, let's figure out what we need. Now, the first thing we need to know to do this is we need to know the number of stars in the galaxy. You multiply that by the fraction of those stars that have habitable planets. You multiply that by the fraction of habitable planets that actually form life. You multiply that by the fraction of planets with life that eventually form intelligent life that could form a civilization. You multiply that by the fraction of intelligent life that could do interstellar communication, and you multiply that by the fraction of the star's life that they actually were able to communicate. So, we're going to go through each of these terms. This last one is a little bit confusing. Let's imagine that a star lives for 10 billion years, but they're only around to communicate for 1,000 years of that 10 billion years. If we miss that 1,000-year window, then we don't see them. So it's kind of like the civilization could have risen, been able to communicate for a while, and then fallen, and now we can't see them anymore, and we just missed the time. So that's that bit. We'll go through it all again. Let's start. So the first question you might ask is, do we know any of these numbers? Or are these all we don't know? Let's find out. The first one is, we definitely know the number of stars in the Milky Way, because we've taken pictures of the Milky Way, we've studied them, we've looked at images from various satellites and telescopes, and we conclude that there's around 400 billion stars in the Milky Way. It gets a bit murky as you get to the very low mass end of it, where they kind of like, is that really a star? But it's around 400 billion stars in the Milky Way, which is a lot, but we know that number pretty well. Second thing is, we know that around half of stars are potentially habitable. Sorry, about half of stars have potentially habitable planets. As we said, we know that from looking at the statistics of the planets we can see, and then inferring how many there would be where we can't see them. It's around half. It could be a quarter, it could be 3/4, but we kind of know that reasonably well. We're not off by factors of 10, maybe factor of 2, so that's pretty good. The fraction of habitable planets that form life. This one's going to take a bit more conversation. So we want to know the fraction of planets that are potentially habitable that actually form life. So how do we figure that out? Well, the first problem is there's no broadly accepted theory of abiogenesis. There's no broadly accepted theory of how life first forms. People are working on it. There's various theories. Nothing's been experimentally shown, and nothing is broadly accepted. Although work is proceeding in this area, and it's quite interesting. I would say it's not done yet, but it might be close. So this leads us to the most pessimistic model, right? So it's like, I'm going to come up with the most crazy, most pessimistic model that I can think of how life could form. And it's like this. We know that there's, from Bennu, we know that there are amino acids in comets and asteroids. Imagine they're all crashing to the Earth, and now we have amino acids on Earth, and these amino acids, if they align up just right, if they connect themselves just right, they could form, they could form a bioactive molecule that could then begin reproduction. And so all that has to happen is these amino acids have to align themselves at random just right. Now you calculate the probability of that. It's stupidly low. It's something like it will happen on a planet 1 in 10 to the minus 50 times. 1 in 10 to the minus 50 is so small that you may as well say it never happens. It's a number that is inconceivably unlikely. It's not actually zero, so you multiply it by the number of stars in an infinite universe, you get an infinite number of planets with life on it. So if this was the case, we still get life on Earth, no problem. It's just that we won't find anywhere else with life, even though there's an infinite number of planets with life in the broader universe. That is the absolute most pessimistic model. You're not going to find biologists who say that's likely, because that's stupidly unlikely. But we're just throwing in there as the most crazy, most unlikely number we can come up with. Now we can think about the most optimistic model. The most optimistic model, and a lot of people working in this area kind of lean in this direction. Natural catalysts greatly increase the density of amino acids, naturally form membranes, and radically increase the probability of bioactive molecules forming. There are as of yet unknown chemical processes that greatly enhance the probability you're going to get a proper RNA or DNA molecule. Consequently, basically it'll always happen. If you get the right environment, you give it a few million years, it's going to happen every time. So that's the range we have. From it nearly never happens, or it never happens, to it always happens. That's our range of knowledge. If you really like what we actually know, that's our range of knowledge of whether or not the fraction of time that life forms given the right environment. This is, like, in other words, we have no idea. This is really, now, it's an area of active research. I hope that by the time it's going to be like any minute now, it's going to be obsolete, and that we're going to have a really good idea. Do we know anything else? Do we have any relevant data? Well, a couple things that people have observed that may or may not matter. The first one is that naturally occurring amino acids are found equally in left-handed and right-handed forms. They're identical other than their symmetry. Life on Earth only uses left-handed amino acids. So at first glance, this seems super unlikely. That would lean toward the it never happens thing, like how in the world would it happen? But there appear to be some chemical processes that might favor left-handed over right-handed. For example, polarized light from the sun might break down one a little bit more than the other. This is speculative, we don't know, but that's why it's an area of ongoing research. So you might say that, it's all left-handed, it's a smoking gun, it's all impossible. How would any kind of chemical process select right from left? There's a few hints that maybe there are things that could separate right from left. Maybe this isn't the proof that life is impossible that you think it is. I mean, life can't be impossible. We're here. Life is very unlikely. All right. The other observation is that life on Earth formed very early, right, like at the tail end of the heavy bombardment. Like the first time you get liquid water on the Earth practically after the heavy bombardment ended, boom, we got life. Like it was really, really quick, relatively speaking. There's some error bars on that, but it's relative to the age of the Earth, life formed right away. So you could say, well, if it formed right away, that implies that it's crazy likely. It's just waiting for the chance to start. As soon as you're not like bashing it with meteorites and melting the rock, it's going to form life. That would say that life is probably really likely, way, way, way more likely than this 10 to the minus 50 number. On the other hand, it could be that life could only form during a tiny little window at the beginning of the solar system, and the vast majority of planets that go through the solar system never form life, but the very, very, very few, like the Earth, only could form them during that narrow window. And so maybe the fact that it happened early just tells us that that was the only time the conditions were right and not that life is likely. So we've gone through these two, and one is arguing for super low probability, one's arguing for super high probability, and both of them you can kind of see that, well, maybe there's ways around it. So we're still uncertain. Without a good theory, it's hard to quantify the number. We don't have a good theory. We don't know what happens. It turns out that nowadays, many experts estimate or guess that the unlikely number is more like 10 to the minus 6 rather than 10 to the minus 50. I don't know how useful that number is. For the sake of our conversation, I'm going to stick with 10 to the minus 50, but we'll see later. If you change it to 10 to the minus 6, it wouldn't matter much. It would give you the same kind of result. But just know that this question is super, super uncertain, and there isn't a real broad consensus on what the lower limit probability should be, although a lot of people will say 10 to the minus 50 is stupid. It's way too small. Yes, it's a stupid theory. It wasn't meant to be serious, but it's the least likely model I could come up with, and that people have come up with. Okay, so do we know anything else? If like we could get ourselves out of this mess, we could rule out the 10 to the minus 50 numbers, move the probabilities way, way higher. If we could find any other place in the universe where life formed, that would like radically reduce our uncertainties. We would know so much more than we know now, which is why there's a big effort to try to find life not on the Earth. Did life form anywhere else? If it did, then we learn a ton. That 10 to the minus 50 number is like completely ruled out, even though we all think it's dumb. And you move up to much, much, much higher probabilities. So where can we look? We can look at our solar system. There's subsurface oceans, like on Europa and Enceladus, there's Enceladus, that may be habitable now. There's liquid water, there's volcanic activity, there's mineral transfer. There's a lot of reasons to believe that Earth life could survive in these places. If that's the case, did life evolve in these places? If the probability is close to 1, the answer is going to be yes. We're going to find life on Enceladus. We're going to find life on Europa because we think the conditions, we're not sure, we think the conditions may very well be right for life to survive and therefore form. So, the Europa Clipper mission is going to Europa. It's going to verify that it actually is habitable, that the story is right, by determining the size of the subsurface oceans, and it's going to analyze geyser chemistry and see whether or not there are organic chemicals in there. That doesn't mean biological chemicals, but chemicals that could be biological. What the composition of the water in the subsurface oceans is, and so this is very exciting as a first step to getting to where we might start to think about, could there actually be life in these subsurface oceans on moons like Europa and Enceladus? In our solar system, Mars, we know Mars had a period of time where it really looks like Earth-type life could have lived on Mars. There was oceans, there was weather, so why not? So the Perseverance rover is looking for signatures of past life. It's driving around, it's got its instruments, and it's found a few clues. Most even this summer, they're like, we don't understand this particular formation in these rocks. When we see these kind of formations on Earth, it's because of life. So we don't know. We can't tell for sure, but kind of looks like it. Maybe it's the best. It's the closest we've gotten. So Perseverance is suggesting maybe there was once life on Mars. If so, that'd be incredibly exciting. We can't know for sure until we bring samples back to Earth. So the Mars sample return mission is being planned and being worked on, and it, in 10, 15, 20 years, depending on priorities and budgets, will bring back samples to Earth to study. So we can try to understand, was there once life on Mars? If there was, and if it formed there independently of Earth, that changes everything. Then all of a sudden we know so much more about the probability of life forming given the right conditions. There's other places we can look at planets. Exoplanets. James Webb Space Telescope is doing infrared transmission spectroscopy of planets around nearby stars. Remember what you do? You take the spectrum of the star plus the planet. Then you take the spectrum of just the star when the planet goes behind, the star. You subtract them, you get the spectrum of just the planet. And from that, you can start to look at the composition of atmospheres. Why do that? What would learning about the atmosphere tell us? Well, if we find significant non-equilibrium chemistry, that would be a remarkable sign of life. What do I mean by that? Imagine oxygen. Oxygen is highly reactive. You get oxygen in the atmosphere, it's going to react with anything it can find. If there's hydrogen in the atmosphere, it's going to react to form water. If there's carbon, it's going to react to form carbon dioxide. Oxygen is highly reactive. If it finds iron, it's going to form iron oxide. If it sees sulfur, it's going to form sulfur dioxide. Oxygen reacts with almost anything. Any planet that had oxygen is going to lose the oxygen. But we have oxygen in our atmosphere. Why? One reason. That's because photosynthesis from plants breaks down carbon dioxide using the energy from the sun to form plant material and oxygen. And so all of the oxygen in Earth's atmosphere is from plants. If we find a planet with clear signs of oxygen, that would be a smoking gun that there is very, very, very likely life on that planet. So this is something that would be very, very exciting. James Webb is trying to measure the spectra of nearby habitable planets, including the ones we saw around TRAPPIST-1. At most, it's going to be able to measure dozens of atmospheres. Not millions, not billions. So if it finds any, it's only going to find them if that probability of life forming, given the right conditions, is large. But if it is, James Webb SETI is likely to find signs of life. If life is common, if James Webb finds a planet with life, it's going to show that life is common. So this is very exciting. It's excellent work. We're going to learn something. We're going to go from this, we kind of have no clue, to here it is. Now, if James Webb finds nothing, we didn't learn a lot other than, well, it's not one, but it still could be a tenth, and we'd be none the wiser. So it's great, especially if life is very likely. If you think life is super unlikely, all right, so far, no signs of life. So coming back to this, I'm going to put the extreme range, 10 to the minus 50 to 1. Some people might want to put 10 to the minus 6 here. They haven't convinced me, so I'm sticking with the 10 to the minus 50. Whatever. Okay, so the next question is the fraction of planets with life that eventually form intelligent life. So now you've got a planet, it's got bacteria, it's got algae on it. Does it ever form creatures with brains, creatures that are intelligent? Now we know what happened on Earth, but it took 3 or 4 billion years to get to anything resembling intelligence. So apparently it's kind of hard, but we don't know how hard because we only have one experiment, the Earth. But it's not zero, so we know it's not crazy easy. But does it always happen eventually? I don't know. Maybe. Most do. Maybe nearly. I don't know. So we're going to guess. This is a wild guess. Just pull numbers out of the air. Why not? What else are we going to do? 1 in 10 billion to every time. You want to put a different number here? It's a guess. I have no idea. I don't know how to calculate it, so I'm putting those numbers down. Who knows? How are we going to know? We're going to have to start. Well, I don't know how we're going to know. So we'll put a huge range there, and maybe the range isn't big enough. Fraction of intelligent life that can do interstellar communication. So we got intelligent life. We've got creatures that are as smart as us or smarter. What's the probability that creatures that are that smart will figure out how to do interstellar communication? Will develop the technologies capable of doing interstellar communication? I don't know. I mean, most? Seems kind of likely, but this is a guess. We're trying to do, what is it? Alien psychology. I'm sure there's some game theorists, people who've tried to do better calculations than this, but I have no idea. So I'm doing mostly maybe a tenth to all smart creatures invent technology, but maybe they don't. You can imagine a species of really smart dolphins who are like, nope, we don't need technology. Life is great in the ocean. And they just live their entire existence running around being dolphins without ever inventing technology, even though they're super, super smart. Because like, why would I invent technology? I can hunt for fish and life is great. So we don't know. That's a number we're just guessing. I'm going to guess a 10th to 1. It can't be bigger than 1, so I don't know. Finally, the last question is a fraction of a star's life that the communicating civilization exists. Let's spend a little bit more time on this one. So here's some points, here's some things that we know from Earth, and we're going to try and say, based on what we know on Earth, what can we speculate about other civilizations that develop the ability to communicate using radio transmitters and stuff. Interstellar communication is possible on Earth with super powerful electromagnetic beacons. So we've just invented that ability in the last 100 years. So maybe we're a good example to look at, just to come up with some ideas. We've also had the technology to end all life on Earth for around the same amount of time, kind of like 100 years or so. We've been able to communicate with nearby planets, and we've been able to end all life on Earth. Obviously, if we ended all life on Earth, we would not communicate with other planets anymore. And also, we know that our star will exist for a total of 10 billion years, but will permit life, before it gets too hot, for about another 1 billion years. It's possible that super advanced civilizations on Earth, a billion years from now, would be able to do things to keep life from being uninhabitable for another few billion years. Who knows? But let's put a billion-ish years as the longest humanity could continue to exist. So you get this pessimistic idea. We're going to blow ourselves up any minute now. Somebody with nukes is going to start a third world war, and we're just all going to die. And it might happen tomorrow. So the pessimistic view is that, and that might be really common. Anybody who invents radio communication also will invent nukes, and anybody who invent nukes will pretty quickly use them and destroy their whole species. That's very, very likely. So pessimistic, civilizations that can communicate will blow themselves up within 100 years of being able to communicate. That's the most pessimistic view. It just happens. That's how intelligent species are. It's game theory. It's going to happen. Or an optimistic view is that, so then we get that number is 10 to the minus 8 as the pessimistic number for FL. The optimistic view says civilizations that can communicate also can survive as long as their star lets them. Right? They're going to be people who can invent communication. In reality, they're going to be too wise to blow themselves up. I mean, the reality is we could say, look, the vast majority of people would never blow up the Earth. And we also know it's risky enough that we've got control over the very, very few who would. So the reality is we're not going to blow up everybody. We're too wise for that. And so would any other civilization that gets far enough to invent nukes. They're also not going to use them. So we're safe. That would say that, it took us 4 billion years to get to this point. The sun will last another billion years before it starts making life unlivable. So call it a billion years out of 10 billion years. So 10% of the life of a star, civilizations can communicate. So of all the planets that form life, 10% of them are actually able to communicate right now. That would be assuming that civilizations last a billion years once they form. Seems optimistic? That seems pessimistic, but that's going to be our optimistic and pessimistic range. So here we go. These are our estimates for all the numbers. Some of them are just guesses. Some of them are reasonable. We only have useful measurements on 2 of them. Number of stars in the Milky Way, fraction of stars in habitable planets. There's work being done on this field right now, trying to figure it out. Both theoretically, how does first life form? Observationally, is there life anywhere else in the galaxy? The rest of these, we don't really even know how to do the experiments on them yet. But let's go ahead and use these numbers. How many civilizations are there in the galaxy? Let's look at the minimum number and the maximum number. I think you already can guess what it's going to be like. So, the modified Drake equation, we multiply them together. So the pessimistic number is 400 billion. There's 400 billion stars in the galaxy. Half of them have planets. The probability of life forming, if it's habitable, is like virtually impossible. The probability of that life forming an intelligence is also virtually impossible, but less virtually impossible. Only 1 in 10 billion. Was FC? That's the probability that they'll learn how to communicate. 1 in 10. And then, but they're going to blow themselves up as soon as they learn how to communicate. So that would put us at 2 times 10 to the minus 58. In other words, none. Right? 2 times 10 to the minus 58 in our galaxy, that's none. That's 0. It never ever happens. I mean, it happens, but you need trillions of trillions of trillions of visible universes before you even find one other civilization. So it is operationally 0 from the point of view of ever finding any. Now, if this number is wrong, if you want to make this number bigger, maybe it's 10 to the minus 6, then maybe this is only 10 to the minus, 10 to the minus 50, no, 10 to the minus 16 or 10 to the minus 14. It's still none, right? So even if you change this number to something more likely, like experts say, no, you're crazy, Netherfield is 10 to the minus 6. You put that number in, it's still none, right? At the pessimistic end of the scale, we'll never ever find another civilization because there aren't any. There are, but they're so far away, light will never get to us from them. So forget it. The optimistic number, however, is very different. You put the biggest numbers in all those, you say, well, there's 400 billion stars, half of them have planets. Anyone that has a habitable planet forms life. Any planet that forms life eventually forms an intelligent life. Any intelligent life eventually learns how to communicate, and they last on their star for 1 billion years. That would say there are 20 billion civilizations in our galaxy. In other words, the galaxy is teeming with life. Now, none and teeming with life, that was the range we kind of knew it had to be before we started doing this math. In other words, the Drake equation is mostly just confirming we have no idea. We have no idea whether or not there is any life, intelligent life, communicating life in our galaxy. We don't know. We just don't know. There's another argument that people use that might be interesting to the question, is there anyone else out there? Imagine, it's just called the Fermi paradox. Imagine that a civilization decides to colonize the galaxy. Okay? They want to, for whatever reason, they say, we want to colonize the galaxy. It'll be great. Maybe they're a rich, tech-savvy billionaire with strange ideas. And he's also super smart and talented. And he's like, I'm going to colonize the galaxy. I'm going to spend my fortune to do that. Well, let's imagine that this civilization that's for some reason decides to colonize the galaxy. Assume that they slightly exceed our current technology. These aren't technology. They have technologies we can think about, and we could work on them if we had the money, but we haven't done it yet. So it's kind of like 20 years from now-ish technologies, things that we could in principle do, we just haven't bothered to do it. In that case, let's say we build a nuclear fission-powered spacecraft that's going to try and go to the nearest star. It would take that nuclear-powered spacecraft something like 50,000 years to get to the nearest star. We don't know of any technologies that could do it much faster than that, so that's not a crazy number. So let's imagine it's going to take 50,000 years to get to the nearest star for this other civilization. In that case, if they go to the nearest star and the colonies there build more ships and send them out, and the colonies there build more ships and send them out, at that rate, this kind of exponential growth, it would take about 1 billion years to colonize the entire galaxy. So, well, how would they do it? Well, there's some kind of science fiction options we can imagine of how they might do it. It might be they're going to use generation ships. That is, they build a giant spacecraft, they put, 5,000 families on this spacecraft, and they send them out. And 1,000 generations go by on the trip, or 2,000 generations go by on the trip. And 2,000 generations go by, they arrive at their planet. Somehow they've managed to stay sane and haven't blown each other up, and still committed to colonization. They get to the nearest star, they colonize it there, they build a new set of ships and send those out. That's the generation ships idea. We don't think that humans could psychologically do it, but we don't know the psychology of these aliens, so maybe they can. Or maybe they've invented some sort of cryo freeze or some other stasis. You can freeze people. You can, I don't know what they could do. Something. That's pretty science fiction-y. So that you put them to sleep, they get to the destination, they wake them up. Science fiction story. I don't know how you do it. The most likely version, and it's getting more likely now, is that crazy awesome tech bro has invented AGI robots that can build more robots. And he says, yes, I can't colonize the galaxy, but my robot children can. And so he builds a spacecraft, fills them with AGI, artificial general intelligent robots that can build more robots, that can repair each other, gives them lots of raw materials, sends them off. They get to the nearest star. They mine the asteroids there. They build a whole bunch more of themselves and send those off. In 1 billion years, the whole galaxy has been colonized by these artificially intelligent robots. Doesn't matter. The whole point of the Fermi paradox is that if just one civilization had somebody or decided for whatever reason to try to do this and were successful, then in 1 billion years, the entire galaxy would be colonized. Now, the universe is 12 billion years old. There are stars that have lived their entire 10 billion years life and blown up again. So there's no particular, if life can exist now, if you can have civilizations now, you would have just as many civilizations 1 billion years ago. So if the galaxy is teeming with life, if there's 20 billion civilizations in the galaxy, at least one of them is going to have somebody who would say, I'm going to build a fleet of robots and colonize the galaxy. Right? Just one civilization started this 1 billion years ago. They would have arrived and colonized us by now. Right? It just takes one. It takes one civilization to decide to build AGI robots that can repair themselves and build new robots and send them out into space. And within 1 billion years, the entire galaxy is full of these robots. But we don't have any compelling evidence of alien visitors. Like, there's no signs that alien visitors are here. So where are they? I mean, right? There's people throw hubcaps in the air and take pictures of them, or they, see some other weird plane at a long distance and get confused. But besides that, UFO observations, there's no real compelling evidence of alien visitors. So, if just one civilization had evolved and started 1 billion years ago, they would have arrived and colonized here already. We would have been teeming with these AGI robots already. We don't have any compelling evidence of alien visitors. So why not? What's going on? There's a few options. Number one, it's very rare for intelligent life to want to colonize. It turns out that something about, game theory, something, evolution, something, wanting to colonize with robots is super, super, super rare. So even though there's 20 billion civilizations out there, none of them would have somebody who actually wants to do this. I don't buy that, but it's a possibility. It turns out that colonization is actually impossible. I'm like, oh yeah, we'll just build a ship, we'll put robots on it, they'll travel 50,000 years when they get there. No, they're going to break down. Things are not going to work. You're not going to be able to bring enough spare parts. They're not going to be able to keep repairing themselves. It's just simply impossible. Even if you wanted to. Even though it seems possible, it isn't possible. You can't build machines that will last for 50,000 years. You can't even build machines that will repair the machines that will last 50,000 years. Forget it. This colonization can't be done. Maybe that's true. So maybe the galaxy is teeming with life and they can't get here because it's actually impossible. Possible? I don't know. Next possibility is there's something out there that stops them from coming. Maybe there's a galactic police force, call it a United Federation of Planets, which is out there and they say, don't let any undeveloped civilizations know we're here. Maybe. I don't know. Possible. Okay. Maybe there's like crowds of hunting robots that some other civilization made that tries to catch any colonizing robots and kills them all before they can get here. And that's what's going on. And the universe is teeming with life, but anybody who tries to leave their star system gets attacked by interstellar sharks. I don't know. Or there just aren't any other civilizations out there. Like, why don't we see any other civilizations? Because there aren't any. Because life is super unlikely. I don't know. We don't know the answer. Let's keep watching. But this is the Fermi paradox, and it is kind of relevant. Let's turn it around. Let's say instead of saying we're just going to try to theorize about the number of civilizations, why don't we just go try and measure it? Like, instead of wondering how many civilizations are going to communicate with us, let's just go look for civilizations. So it turns out that civilizations emit radio waves. That's kind of our idea anyway. At least we do. We emit quite a bit of radio waves. Could we detect a civilization just like ours that was orbiting a different star? Well, let's look at a few scenarios. How far away would our best planned radio telescope detect them? So this is a paper that was written, and they are comparing it to using what's called the Square Kilometer Array, a huge radio telescope that's funded and is being built. Canada's part of it. So if the SKA was looking at a distant planet, could they detect various types of signals? That's the first one we're going to consider is all the cell phone towers on Earth combined. So let's imagine there's a planet just like the Earth, and they have a cell phone network just like the Earth's, and the radio telescope is going to look for cell phone signals, and it's going to look at the power from all of the cell phone towers on the entire planet combined. Well, we know the calculations show that we could detect such an array at around a range of 4 light years, which is not even to the nearest star. And television has similar range. So we can't detect aliens' TV signals, and we can't detect their cell phone signals. That might think, well, we can't detect them with radio. And that's with an incredibly sensitive radio telescope, getting close to the limit. So probably going to be really hard to detect kind of accidental leakage. But there's other options. Case number 2, radar. These really, really powerful pulses that swing around looking for enemy planes, using these radars to look for the distance to nearby asteroids, things like that. Super powerful radio waves. We send out as powerful a ping as we can and listen for the response. If one of those pings happen to be pointed at the Earth, let's say the aliens have this powerful radar, and they're trying to search for enemy planes, or they're trying to measure the distance and the speed to the asteroids or something. If that radar happened to be pointed exactly at us, could we detect it? Turns out that the range of those, because those are really powerful pulses, the range of those would be something like 12,000 light years. That's a long way. That's a part way across the galaxy. So, yeah, radar pulses, alien radar pulses, is something that we probably could detect from a lot of planets. So we might be able to detect alien radar. That's a thing to look for. What are we looking for? Bing, 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 pulses. Okay. Last possibility, intentional beacons. What if the aliens want to be found? Back in the 1970s, some scientists used Arecibo to send super powerful signals to a few nearby planets saying, hey, if you're there, we're here. Hello. But we haven't been listening since, so they may have answered, and we don't know. A pulse like that would have a range of also around 12,000 light years. And that's also partway across the galaxy, and these can be made even more powerful. So people think if we're going to try and find aliens, we're looking for aliens who want to be found, who send beacon signals to nearby planets saying, hello, do you want to talk? Hello? And if we get the signal, then we can reply and maybe start a conversation. If they're 100 light years away, then the ping time's 100 years. It's going to be kind of slow, but who knows? But there are people who are trying to search for extraterrestrial intelligences. They're trying to look for, are there aliens out there who are either have powerful radars or are trying to communicate with us or something. This has been going on since the 1970s. There have been ongoing attempts to find radio emissions from alien civilizations. Most of these projects are privately funded. Usually governments don't get involved. But there's people who are like, I want to know. I'll give you $20 million. Some use existing scientific telescopes and others use custom-built telescopes. And so far, there's been no definitive signals. There have been a couple, like a single ping, like in the late 70s. Ping! Really bright. Came and gone. Never came back. Don't know what it was. Was it aliens pinging? Was it some astrophysical event? We don't know. But there's been no definitive signals, and this research is continuing. So, what do we conclude? Is anyone else out there? Yeah. We don't know.